This is the fifth talk related to basic electronics in clinical neurophysiology. The purpose of this talk is to explain a few concepts about inductors relevant to the neurophysiology board examination. These concepts relate to two issues. The first issue is the use of inductors in electronic circuits of the EEG machine. Inductors in the electronic circuit of the EEG machine are used as transformers and rectifiers. The purpose of transformers in the EEG machine are to unground certain components of the equipment and to adjust the voltage to the need of different components of the equipment. Rectifiers are used to transform alternating current into direct current. The second issue that makes inductors relevant to neurophysiologists relates to the processing of the EEG signal. Inductors are used to build filters. Inductors are used to manipulate the EEG signal because of their ability to selectively allow electricity to go through or be blocked according to its frequency. This talk will be conducted in a question and answer format. Here goes the first question. Which of the following is a component of an inductor? A. Plates, B. Insulating material, C. Dielectric, D. Solenoid. An inductor consists of a continuous coil wire called a solenoid. So the answer to this question is D. Solenoid. Next question. The symbol for an inductor is A, B, C, D. The most used symbol for inductor is a straight line with multiple humps, but often inductors are represented by schematically drawing them as simplified coils. So the answer to this question is A. Which of the following is not a function of inductors in the EEG machine? A. Protect patient against electric shock. B. Modulate equipment voltage. C. Modulate EEG recording. D. Amplify EEG activity. I have already briefly mentioned this issue in the introduction of this talk, but I'd like to dwell on it for a few minutes more since it will provide structure for our talk. This figure you are looking at is a representation of an EEG model. You can tell it is an old EEG machine model because of the presence of a writing unit. I like to use this representation as a model for our talk about EEG components because of its simplicity. So I will use it to show you all the contributions of inductors to the EEG machine. In this frame, I have introduced inductors at all places they are used in an all EEG machine. Inductors are used to adapt the voltage coming from the wall socket to the need of the equipment. When used in this fashion, inductors are called transformers. They are also called transformers when used for safety. Transformers contribute to safety by isolating certain areas of the AD machine from the ground. They are used in conjunction with diodes to turn alternating current into direct current, in which case they are called rectifiers. And they are also used in conjunction with capacitors in order to build filters. And what is most interesting is that all these functions of the inductors are achieved by exploiting one characteristic of electricity, and that is the two-way interaction between electricity and magnetism. So the answer to this question is D. Next question. All of the following are true regarding the right-hand rule for magnetism, except A. Current travels in the direction of the axis of the thumb. B. The magnetic force is oriented at the curl closed fingers. C. The magnetic field is oriented in the direction of the axis of the thumb. D. The right-hand rule for magnetism works for wires. The right-hand rule is used to explain some of the characteristics of electricity and magnetism. If electricity flows in the direction of the axis of the thumb, as indicated by the magnetic arrow, a magnetic force will be created, with the vector of this force traveling in the direction of the curled fingers, as indicated by the blue arrows. This force will only occur when electricity is flowing and the voltage in the wire is changing. This magnetic force will create an electrical force that will oppose the electrical force originating it, as indicated by the yellow arrow. This electrical force is referred to as self-induction. In addition, if a second wire is brought adjacent to the wire originating the magnetic force, the second wire will also develop a current. This current will result from the electromotive force produced by the magnetic force on the second wire. The electromotive force in the second wire will occur in two situations. One that we have already addressed, and that is when current is changing in the primary wire, and the second situation that will produce an electromotive force will be if the second wire is being moved across the magnetic field of the primary wire. That will occur even if the current is not changing in the primary channel. So the answer to this question is C. Next question. Current in a wire connected to a power source, that is wire A, will induce a current in an adjacent wire, that is wire B, only during the time that the current is changing in wire A. A true, B false. When current is changing in the primary wire, color green in this frame, current will occur in the secondary wire, color magenta in this frame. When current is not changing in the primary wire and the secondary wire is still, current will not occur in the secondary wire. When current is not changing in the primary wire, but the secondary wire is moved across the magnetic field of the primary wire, current will occur in the secondary wire. So the answer to this question is B. False. Next question. Current in a wire A connected to a power source will induce current in an adjacent wire, that is wire B, if wire B is being moved across the magnetic field of wire A. A, true, B, false. This frame is the same frame that I presented to you to answer the last question. I placed this question here again to emphasize this point and to tell you an analogy. The analogy is of two people sleeping in a bed. If one is active, the other one wakes up. So the answer to this question is true. Next question. Transformers are used to A. Protect patient against electric shock, B. Modulate equipment current, C. Build filters, D. All of the above. So inductors convert electricity into magnetism and magnetism into electricity. This is the basis of transformers. Transformers allow us to transform high voltage coming into a transformer into low voltage coming out of the transformer, or to go from low voltage coming in to high voltage going out. Notice in this example that the number of turns of the coils in each transformer is directly related to the magnitude of the voltage coming in and going out. More turns, more voltage. And the last use of transformers is to transform ground electricity to on-ground electricity, thus providing safety against electric shock. So the answer to this question is A. The reason for that is that transformer modulate voltage, and that although inductors are used to build filters, transformers are not. Next question. Inductors allow slow activity to go through while preventing fast activity from going through. A, true, B, false. Inductors behave as filters, allowing slow activity to go through while blocking fast activity. Direct current travels uninterrupted and unmodified through a completely charged inductor. Direct current having zero frequency and thus is subject to zero resistance. But when dealing with alternating current, as frequency increases, so does resistance. This is expressed in this frame by the blue line. So the answer to this question is true. Next question. Inductors convert AC to DC by slowing the build-up and winding down of current. A, true, B, false. Alternating current is here represented as a sinusoidal wave. Direct current is represented as a straight line. The reason for this is because in alternating current, current travels back and forth in the circuit, whereas in direct current, current travels only forward. The conversion of alternating current to direct current starts with a diode. Diodes can be built to allow only the electricity traveling in one direction to go through. At this point, an inductor is needed for further modifying alternating current to make it direct current. In the top segment of this frame, I have used solid lines to indicate the result of using a diode on alternating current. In the bottom, I have made the same representation but made them with dashed line to show you how an inductor transforms the waves into a straight line. So what the inductors does is to flatten the waves by prolonging the duration of the wave at the expense of its amplitude. This occurs by opposing the buildup of charges when the inductor is charging and slowing the dissipation of charges when the inductor is discharging. Ultimately, a straight line emerges, consistent with direct current. An interesting question is how can this be done? To picture how homes become straight lines, I like to use an analogy. I imagine that one little man on each side of the curve is pushing it away from the center. As you can see in these consecutive frames, the line as it is pushed becomes more and more straight. The little men represent volts generated by magnetism that oppose the change in ongoing current as the current is built up and oppose dissipation of current as the current is dying out. We will talk more about this in the following minutes. So the answer to this question is true. Next question. The symbol for the amount of inductance in equations is ALBICRDH. One thing is for sure, that I was already taken by current. So they went for the letter L. Maybe because it is the last letter of coil, but who knows? So the answer to this question is A. Next question. Inductance has only one simple definition. A true, B false. Inductance can be defined as the property of electrical conductors by which a change in current throughout the electrical conductor induces an electromotive force. In the conductor connected to the power source called the primary conductor, and in a nearby conductor called the secondary conductor. The electromotive force generated in the primary conductor is called self-inductance. The electromotive force generated in the secondary conductor is called mutual inductance. The mathematical expression of this definition has two formulas. One for self-inductance. The one for self-inductance is self-inductance can be defined as the electromotive force present in a primary circuit resulting from the subtraction of the voltage produced by inductance from the voltage supplied by the power source in relation to time. And the definition for mutual inductance is the electromotive force generated in a secondary circuit brought about by the magnetic coupling between the two neighboring circuits, multiplied by the change in current in relation to time. The magnetic coupling is labeled M. But this is not the only definition. Another definition of inductance is inductance is the flux linkage divided by current and multiplied by a constant. The constant converts the rate of change of flux in lines per second into induced volts. And still there is a third definition. Inductance can be defined as the ability of an inductor to store energy in the form of a magnetic field. No doubt this last definition is the simplest. Nonetheless, this simple definition requires a complicated formula that we will also address a little bit later. So the answer to this question is false. Next question. Induction effects on a primary circuit consist of all of the following except A. Slow down the current built up when electricity starts flowing. B. Maintenance of the magnetic field when current flow is stable. C. Slow down current dissipation when electricity is turned off. D. Convert electricity to light. In this frame, I am representing an odd-shaped circuit with an inductor represented by a circular structure, a 5-volt battery, and a switch. The switch is open. I will call this circuit the primary circuit. In this frame, I have added a voltmeter measuring the primary circuit. As you can see, the voltmeter indicates 0 volts because, as we mentioned before, the circuit is open. In the next frame, I will introduce electricity into the primary circuit. I will depict this by closing the circuit. The closing of the primary circuit allows electrons to flow through the circuit. The aqua arrow represents electrons flow and the direction of the flow. Notice at this point the voltmeter is showing an increase in voltage, but only of 3 volts. The reason voltage has not gone up to 5 volts immediately is because as electrons flow through the inductive element of the circuit, some of the charges in the electrons are converted into magnetic force. I have represented the magnetic force as arching green arrows around the circular segment of the wire. The direction of the vector of the magnetic force is governed by the right-hand rule, the one we alluded a little bit earlier. the magnetic force produces a current that opposes and slows down electron flow through the wire of the primary circuit. I am representing this current created by the magnetic force as a curved bright blue arrow close to the circular portion of the primary circuit. But as the magnitude of the electricity produced by the battery continues to push, the voltage of the circuit will increase. This is indicated in this frame by the voltmeter going from 3 to 4 volts. The other consequence of this increase in voltage is an increase in the magnetic force around the coil. I have depicted the increase in magnetic force by adding larger circular arrows around the circular segment of the core. Ultimately, the voltage in the battery and the voltage in the primary circuit becomes the same. And once the circuit voltage is the same as the voltage in the battery and no further increase in voltage is taking place in the circuit, the magnetic force becomes a magnetic field, which I have represented in this frame as a gray cloud surrounding the circular portion of the circuit. And also, as a consequence of the disappearance of the magnetic force, the force opposing the flow of current propelled by the battery also disappears. This state of affair will continue, that is, current will keep flowing untouched until the switch is turned off. At this point, three curious things will happen as the magnetic field disappears. First, the voltmeter will not go to zero as it would happen in a circuit without an inductor. The reason some voltage, for example 4 volts, will appear in the voltmeter is because some of the voltage stored in the magnetic field will incorporate to the circuit. Simultaneously, a second thing will happen. Again, a magnetic force will appear. The vector of this new magnetic force will travel in the opposite direction from the vector created by the original magnetic force. The third thing that will happen is that a current will flow for a short period of time. This current will be in the direction of the previous current generated by the battery. This current will flow in the primary circuit. I have presented this current by a white arrow close to the circular portion of the primary circuit. But as the voltage continues to drop, the magnetic force begins to dissipate and then disappears. The voltmeter at this time will indicate 0 volts. I know this explanation has holes, but it is the best I can do. So the answer to this question is D. Next question. Induction effects on the secondary circuit consist on all of the following except A. Generating an electric motive force when current is changing in the primary coil. B. Generating an electromotive force when power is turned on. C. Generating an electromotive force when power is turned off. D. Generating an electromagnetic force all the time. To explain what happens in the secondary circuit, I will initially represent a primary circuit at the time that the magnetic force is present. I am representing the magnetic force as it being produced by current beginning to flow, because whether the current is beginning to flow or dying out is the same for our current explanation. The important thing for this explanation is that the magnetic force is present. I will now introduce a secondary circuit. Here I am representing it in red. In addition to the secondary circuit, there is a voltmeter connected to it. The voltmeter at this point is marking 0 because at this junction no portion of the secondary circuit is exposed to the magnetic force because it is too far. But once any portion of the secondary circuit becomes in contact with the magnetic force, three things will happen. First, a voltage will be generated in the secondary circuit. This is indicated by the voltmeter of the second circuit going from 0 to 1. Second, the voltage will generate a current, here expressed as the magenta arrow by the side of the secondary circuit. And third, the current will produce a magnetic force in the circular portion of the secondary circuit. The vector of this force will be in the opposite direction than the vector of the magnetic force in the primary circuit. In this frame, the magnetic field of a secondary circuit is represented by yellow and aqua arrows. Ultimately, the magnetic force will disappear in two situations. The first situation is when the current stops fluctuating in the primary circuit. In this situation, the magnetic force is substituted by an unchanging magnetic phenomena which we have chosen to call a magnetic field. This is expressed in this frame by the disappearance of all the arched arrows. The second situation is when, as a consequence of turning the switch off and all current disappearing from the circuits, the magnetic force also disappears in the primary and secondary circuits. So the answer to this question is D. Next question. Inductance is the property of an electrical conductor by which a change in current through the electrical conductor induces an electromotive force in both the conductor itself, that is self-inductance, and in any nearby conductors, mutual inductance. A, true. B, false. If you recall, we have used this statement to define inductance in the past. Our understanding of the answer to this question is crucial to our understanding of induction. So please pay attention. The effects of inductance in a direct current circuit needs to be studied in three different situations. When the current is turned on, when the current is flowing at a steady rate, and when the current is turned off. Let's first talk about what happens when the current is turned on. This frame depicts what happens in the primary and secondary circuits as the voltage is increased. Current is flowing in the circuit. A magnetic force is generated. The magnetic force produces a current in the opposite direction as the current produced by the battery. And the magnetic force also induces an electromotive force in the secondary circuit. The electromotive force in the secondary circuit creates a current. The current triggers a magnetic force in the secondary circuit. This current also affects the primary circuit. In addition to understanding what are the effects of inductance in a DC circuit when current is increasing, we need to understand the effects of inductance in a DC circuit when current is steady. In this frame, I will again try to depict what happens when current is steady. When current in the primary circuit is flowing steadily, a magnetic field develops. The magnetic field is where energy is stored. I have represented this field as a gray cloud around the primary circuit. The magnetic field does not produce a current opposing the current from the battery as the magnetic force did, nor it produces an electromotive force or current in the secondary circuit. So this is what occurs when current is steadily flowing through an inductor. Now, let's talk about what happens when current is decreasing in an inductance circuit. When the switch is turned open, a magnetic force reappears. This magnetic force has a vector in the opposite direction as the vector that was generated when the current was turned on. The magnetic force also triggers a current that, unlike the current that was triggered when the circuit was turned on, this current goes in the same direction as the current that was produced by the battery. In addition, an electromotive force appears in the secondary circuit that produces a current in the secondary circuit. The current again triggers a magnetic force in the secondary circuit. Ultimately, all ceases as the battery is no longer connected to the primary circuit and the energy dies out. So the answer to this question is true. Next question. When a magnetic force interacts with a wire, an electromotive force is created in the wire. A true, B false. In one of the last frames I just showed you, when explaining the last question, I presented this figure to you. The figure represents a moment in the life of current through an inductor frozen in time. I will use set here again to explain to you the way I picture in my head the creation of electricity from magnetic forces cutting through wires, or as a consequence of wires cutting through a magnetic force. This is a fictional account. I will focus at two sites. One where the magnetic force interacts with the wire of the secondary circuit, that is, the area inside the white square. The second, anywhere in the secondary circuit that the wire is not being cut by the magnetic force. I have selected the area that I have enclosed in the yellow square. I will contrast what occurs in the secondary circuit being affected by a magnetic force to what happens in a circuit not being affected by a magnetic force. At this time, I am representing a segment of the secondary circuit not exposed to any magnetic force. As you can see, there are no free electrons. The new figure I have just introduced represents the area in the secondary circuit where the magnetic force is cutting through the wire. How I picture what happens as the magnetic forces cross the wire is, as you can see in this frame. I think of it as a dislodging of electrons from their nucleus. And an attraction force that at the same time that dislodges the electrons, it aligns them in a specific area in relation to the nucleus. This arrangement creates an excess of electrons on one place in relation to another place, thus generating a voltage between the two places. So the answer to this question is true. Next question. An electromotive force produces a current. A true, B false. I will use the same arrangement to answer this question as I did in the last one. I will first analyze what goes on inside the blue square. On the left side of the frame on top, I have represented a secondary circuit not being caught by any magnetic force. On the bottom, you have a representation of the atom in the wire in such conditions. All electrons are going around the nucleus and there are no free electrons. Now I have introduced a yellow square. This yellow square represents a segment of the secondary circuit that is being cut by a magnetic force, but at a location where the cutting is not taking place. I have pointed the place by the arrow. So again, going back to the enlarged yellow square, you can see that the atom represented in the lower part consists of free electrons that are traveling, thus creating a current. Remember, I just presented to you an analogy in order to tell you a way that I remember how inductors behave. The reality is different and more complicated. But there's one thing that you should remember, that the bigger the magnetic force per time, the more electrons will be dislodged. That is a reality. So the answer to this question is true. Next question. The formula below expresses the magnitude of the voltage induced by induction as it relates to the changes in magnetic flux over time. A true, B false. This formula expresses the voltage created by the magnetic force upon an inductor. The E stands for volt or electromotive force. The minus sign is there to account for the fact that the current produced by the cutting of the wire by the magnetic lines goes in the opposite direction to the electrical current produced by the power source. N stands for the number of turns in the coil. The Greek letter corresponds to F, and it stands for magnetic flux. The whole fraction stands for rate of change in relation to change in time. And the last number is a constant. This constant allows us to convert the rate of change in the magnetic force with the voltage it produces. So the answer to this question is A. Next question. Inductance is the measure of an inductor's ability to store energy for a given amount of current flow. A true, B false. When current flows through an inductor, some of the voltage going through it are stored as energy. So the answer to this question is A. Next question. The following formula expresses the potential, that is the inductive capacity that the magnetic field in the primary circuit has to generate voltage in the secondary circuit. A true, B false. I imagine the magnetic field as a magnetic cloud that stores electric energy. The capacity of a magnetic cloud to induce changes in the secondary circuit depends on the factors expressed in this formula. L stands for inductance. As we know, inductance is directly proportional to the relative magnetic permeability constant of the substance within the turns of the wire, the magnetic permeability constant, the square of the number of turns in the coil, and the area inside the coil. Inductance is also inversely proportional to the length of the core. In this frame, I have represented the inside of the core as a cylinder. I have done this to show what I meant when I spoke about the area inside the core. Just think about the base of the cylinder and use its radius indicated by the R to determine the area of the base of the coil. In this frame, I indicated the significance of length. So the answer to this question is true. Next question. Which of the following factors is inversely related to the inductance of an inductor? A. Number of turns. B. Magnetic constant. C. Area of the coils. D. Length of the coil. This question can be answered by a brief look at this equation. Just look at the factor being pointed by the arrow. So the answer to this question is D. Next question. The distance between the plates of a capacitor and the length of the coil are inversely proportional to the value of the device. A. True. B. False. I like to think of induction and capacitance as the reverse of each other. That is, to think of them as the yin and the yang. Hence, I will start with the formula for capacitance that we have introduced in prior talks. I hope you remember this formula from the prior video, but if you don't, you can just look at it in this frame. I will change each term of the capacitance formula for the term related to the induction formula. I will do this to show you its similarities and its differences. The C for capacitance in the capacitance formula, I will substitute for L in the induction formula. The L stands for inductance. The ER representing in the capacitance formula electrical permeability value of a given substance, I will substitute by the Greek letter M to indicate magnetic permeability value of a given substance. The dielectric constant in the capacitance formula, I will substitute by the magnetic constants. The fraction constituted by the area divided by the distance of the plates, which is characteristic of the capacitance formula, I will substitute by the fraction of the area of the circumference of the core divided by the length of the core. The big difference is that the inductance formula has an extra factor, and that is the square of the number of turns. So the answer to this question is true. Next question. Inductance has the same relation to current than capacitance has to voltage. A. True. B. False. As I told you before, I like to think of induction and capacitance as the reverse of each other. Take a moment to look at this formula. Inductance has the same relation to current that capacitance has to voltage. The change in voltage of a capacitor controls the flow of current into the capacitor. The change in current of an inductor controls the voltage stored in the inductor. So the answer to this question is A. Next question. Inductance is proportional to the square of the number of turns in the coil. A. True. B. False. The bigger the area, the bigger the inductance. The more stretched, that is, the longer a coil is, the less inductance. If instead of air or an empty core space, we put iron that has a high magnetic constant, the induction will increase. The more turns per length, the more inductance. I think of the relation between magnitude of inductance and component of an inductor by considering that all the factors that increases the length of the uncoiled wire or adds magnetic value to the inductor increases the inductance of the inductor. So the answer to this question is A. Next question. What is a Henry? A. Voltage second per ampere. B. The unit of resistance. C. Coulombs per volt. D. None of the above. The Henry is the unit of inductance. We can think of it as we think of a farad for capacitance. 1 Henry is the amount of inductance needed to generate 1 volt in the secondary circuit with a current changing at the rate of 1 amp per second in the primary circuit. The formula in this frame implies what I just mentioned regarding a Henry. A permutation of this formula produces the following conclusion. 1 Henry is equal to volts per second and inversely proportional to 1 amp. So the answer to this question is A. Next question. The primary effects of an inductor is on voltage. The effect on current is secondary. True or false? As I told you in the past, most things that are done by a capacitor in a way are done by an inductor in the opposite way. In this frame, I am representing an inductor and a capacitor. I have also introduced a triangle to make reference to Ohm's law. Notice that each value has a different color in the triangle. Electromotive force or voltage is in orange, current or amperes is in magenta, and resistance in ohms is in red. The open circuit in red with the arrow pointing to the closed circuit indicates that a connection is being made between the wires, thus allowing the power source to run. The man and the arrow indicates the effect on the circuit produced by the connection with both wires. The color of the man indicates the primary effect, in this case voltage, since the man is painted in orange. The color of the arrow indicates the secondary effect, that is on current. So as current begins to flow from the battery, inductive forces opposes the increasing current. In this frame, I have represented these forces as the man pushing the current. It is important to stress that the effect on current of an inductor is the consequence of the voltage produced by the interaction between the magnetic forces and the wire. When the current is turned off, as indicated in this frame by going from the green sphere to the red sphere and going from a continuous wire to a wire that is separated, an electromotive force is triggered in the wire by the collapsing magnetic field. This collapsing magnetic field produces a force that sustains the current flowing in the direction it was, driven by the battery just before the battery was turned off. I like to draw the analogy with a car and a winding road. The car being coulombs and the inductor the winding road. As you get to a winding road, you slow down the car. As you come out of the winding road, you speed up the car. Another frequently used analogy is to remember that inductors do not like change. They basically oppose the change in current. They oppose the increasing the current when the switch is turned on, and they oppose decreasing the current when the switch is turned off. Now we can contrast what happens in the inductor with what happens in a capacitor. When current is turned on a capacitor, the progressive accumulation of charges in the plate connected to the anode slows down and makes it more difficult for voltage to increase in the capacitor. When the capacitor is turned off, the release of voltage from the capacitor is delayed and it is in the opposite direction than the previously flowing current. I think of this as a capacitor being like a parking lot in a football stadium and a car being boats. As we all know, it is difficult to get in at the beginning of the game, and it is also difficult at the end of the game to get out. So the answer to this question is true. Next question. Inductors and capacitors store energy. A true, B false. Energy is stored in inductors and capacitors. Inductors have kinetic energy related to the flow of current. Capacitors have potential energy related to volts. The formula to determine the time constant of an inductor is inductance divided by resistance. The formula to determine the time constant of a capacitor is capacitance times resistance. An inductor allows a slow wave to go through. Once an inductor is full, as long as there is no change in current, the inductor becomes a resistance-free conductor. A capacitor allows fast wave to go through. Once a capacitor is full, as long as there is no change in current, the capacitor becomes an infinite resistance conductor. It blocks all conduction. Yet, an inductor holds charges and so does a capacitor. The inductor stores the charges in a magnetic field. The capacitor stores charges in the plates. So the answer to this question is true. Next question. Self-induction and mutual induction of voltage only occurs when the magnetic fields are expanding. A true, B false. This formula establishes the relation between voltage and inductance. If the relation between current and time is not changing, no voltage will be generated. This is expressed in this frame by the rate of change between current and time being zero. If the rate of change between current and time is zero, no voltage will be stored in the inductor. If the rate is not zero, whether it is up or down, voltage will be stored in the inductor. So the answer to this question is false. Next question. The voltage formula for self and mutual inductions is the same. A true, B false. The formula I will introduce in this frame were already presented to you when I talked about the definition of inductance. They represent the creation of voltage as a consequence of induction in the primary and secondary circuits. I will first address self-induction. I hope you remember this figure from earlier in this talk. The reason I am presenting it to you again here is to remind you that despite the battery having 5 volts, the voltmeter immediately after turning the circuit on measures only 3 volts. The formula that expresses this mathematically was also introduced when we define inductance. I hope that at this point the reason for the minus sign becomes obvious. That is because the force generated by inductance has to be subtracted from the total voltage imparted into the circuit by the battery. The formula for mutual induction reflects the fact that voltage is being created in the adjacent circuits, that is, the secondary circuit, which in turn affects the voltage of the primary circuit. In this frame, I have introduced a primary and a secondary circuit influencing each other. I will expand on this concept in the following frames. This frame shows a primary circuit powered by a battery of 5 volts. The current is creating a magnetic force. The magnetic force is decreasing the voltage going through the primary circuit, but has, as of yet, not influenced the secondary circuit. This is expressed by the voltmeter of the primary circuit showing 3 instead of 5, as it's present in the battery, and the voltmeter of the secondary circuit indicating 0. The only difference in this frame from the one before is that the magnetic force of the primary circuit has created a voltage in the secondary circuit. This is reflected by the voltmeter in the secondary circuit going to 1 volt. This frame introduces a magenta arrow to indicate the current arising from the volt just created in the secondary circuit. This current, as it flows in the secondary coil, also produces a magnetic force, but in the opposite direction. This magnetic force induces a current in the primary circuit in the opposite direction and decreases the voltage of the primary circuit. The mathematical expression of this phenomenon is introduced in this frame. As you can see, I'm using the letter M. The letter M expresses a factor that depends on the magnetic coupling between the two adjacent circuits. The negative sign indicates that the voltage in the primary circuit decreases as a function of the magnetic force generated in the secondary circuit. Again, in this case, the force created by induction works in the adjacent circuit by subtracting electromotive force. So the answer to this question is B, false. Next question. Inductors slow down the increase of current when the switch is turned on. A true, B false. This frame represents an open resistor inductor circuit. A voltmeter and an amp meter are connected across the inductor. The data from these devices will be displayed by the side of the V for voltage and the I for current. You can see both of these letters in the frame. In this frame, I have removed the device to simplify the figure and be able to show you what happens easier. I have added on top a switch in 3 stages. The one to your left is open, hence no electricity going through. The one in the middle is closed, hence electricity is going through. The one to your right is open, hence electricity is not going through. The aqua line represents the voltage applied. The area within the dashed lines represent the time voltage is applied to the circuit. The arrival of voltage to the inductor will have one consequence regarding the total voltage of the system. Voltage will be taken away from the circuit to be stored as magnetism. This will only occur while the voltage is changing. Once voltage have become stable, the voltage in the circuit will go back to be driven by the supply from the battery. After the circuit is closed, the same voltage that was taken out and stored as magnetism will go back into the circuit and produce a current in the same direction as the current was flowing from the battery. The arrival of current to the inductor will have one consequence regarding the total current to the system. The rate of current increase will be slowed down while the inductor is taking away volts from the system. Once the voltage is not changing, the current will be stable. When the circuit is open, the current will not drop immediately, since the stored voltage as it's being released maintains and slows down the drop in current in the circuit. I will try to express this in a more pictorial fashion in the next couple of frames. The purple area indicates a change in voltage and current. Through this period, the inductor behaves just like a straight cable with no resistance. The area in blue indicates the time during which voltage is changing. When the current starts flowing to the conductor, the magnetic force created by the current going in one direction causes an electromotive force that makes the induced current opposite. This is represented by the blue man pushing against the yellow arrow. When the switch is turned off, the blue man, as you see, is pushing on the direction of the flow of the electrons produced by the battery. So this is what happens when dealing with resistor inductive circuits. Now let's see what happens when dealing with resistor capacitor circuit, so we can draw the difference and similarities between these two types of circuits. Here we have the same situation as we had before. The only difference is that in this circuit we have a resistor and a capacitor. In this frame I am representing the voltage applied. The dashed lines indicate the time voltage is being applied. In this frame, I am representing voltage. The purple rectangle indicates a time where voltage is stable. In the lower segment of this frame, I am representing current. Initially, as the current is introduced in the circuit, the current reaches its maximum in the capacitor. But as more and more electrons accumulate in the plate, and the plate gets crowded, the deposition of electrons in the plate slows down. This is expressed in this figure by the man pushing against the arrow. When the circuit is open, that is, when the flow of current stops, the capacitor will discharge. The current at this time will be in the opposite direction that was initially flowing, since it is the electrons stored in the negative plate that flow against the direction of the original current that charge the capacitor. So changes will only occur when electrons are being deposited and when electrons are being discharged from the plate. That is, changing in current will only occur during those situations. So the answer to this question is A. Next question. All of the following are true about inductors except A. Inductors store energy as magnetism. B. Inductors obey the right-hand rule for electrical current. C. Inductors allow passage of direct current when fully charged. D. Inductors, when turned off, produce terminal current going backwards. Inductors store energy as magnetism. We have said this previously, but I would like to remind you. Inductors obey the right-hand rule for electrical current. This is an example of the right-hand rule. Notice the direction of the aqua arrow and the green circle with the arrow. Inductors allow passage of direct current when fully charged. Direct current has zero frequency and thus is subject to zero resistance. As the frequency is higher, the resistance also increases. Inductors, when their direct current power source is turned off, produce a terminal current going in the direction that the current was being propelled by the battery. So the answer to this question is D. Next question. Inductive reactance is the force that slows down the buildup of current when a resistor inductor circuit is being charged. A true, B false. I hope you remember this figure from a few minutes ago. The dark curved blue arrow represents inductive reactance. The formula for inductive reactance is voltage divided by current. This formula expresses that reactance inductive is directly related to voltage and inversely related to current. Inductive reactance, especially when dealing with alternating current, can also be expressed as a function of inductance. In this case, we can say that inductance reactance is equal to 2 times pi times the frequency of the current times the inductive of the medium in henries. So the answer to this question is true. Next question. Inductive reactance and resistance cannot be added because they are not in phase with each other. A true, B false. A voltage drop will occur when current is going through a resistor and when current is going through an inductor. But they cannot be added. They are subject to a significant mathematical manipulation. What is important is the fact that as I just previously established, they cannot be added because they occurred in a different time sequence. So the answer to this question is true. Next question. The larger the inductor, the smaller the inductive reactance. A true, B false. Inductive reactance expressed by the letter X and L, as we have seen, is proportional to the size of the wire. Capacitance reactance is inversely proportional to the size of the plates. The bigger the plates, the less the resistance. So the answer to this question is false. Next question. Inductors are used to block DC current while allowing AC current to pass. A true, B false. An inductor will behave like a non-resistance element when current is running at a stable pace. Inductors only influence electricity if voltage is changing. Inductors allow passage of direct current when fully charged. Direct current has zero frequency and thus is subject to zero resistance, as we said before. If the frequency of the current is increased, so is the resistance, because as the frequency of the current increases, the resistance also increases. It is important to remember that the formula I presented to you about inductance is only present when current is changing. In direct current, only when the electrical field is expanding or retracting, while in alternating current, it is happening all the time. I like to remind you also that capacitance reactance is the opposite of inductive reactance. Inductive reactance is zero when the inductor is fully charged and current is flowing steadily. Capacitance reactance is infinite when the capacitor is fully charged. Thus, a capacitor, when powered by direct current and fully charged, does not allow current to go on. On the other hand, when dealing with alternating current, if the current in 1 radian is not enough to fool the capacitor, the current will go on uninterrupted throughout the cycle. Remember that in a capacitor, electrons do not cross the dielectric, but they force the electrons on the other plate to move because of the electrical force generated by the electrons in the plate close to the negative side of the battery. The difference between inductors and capacitors is exploited in the production of certain filters. Inductors will allow a slow current to go through whereas capacitor will allow fast current to go through. So the answer to this question is false. Inductors are used to block alternating current while allowing direct current to pass. Next question. Ohm's law works for induction if we substitute R for XL. True or false? This frame shows current in relation to other factors. As you can see, substitution of XL for R explains the behavior of current in an inductor. The behavior of current in relation to a capacitor is more complex. So the answer to this question is A. Next question. Inductance has the same relation to current that capacitance does to voltage. A true, B false. When an inductor is being used, the behavior of voltage influences current. The answer to this question is A. True. This question, so answered, reflects the writing in Fundamentals of Electroencephalography. Yet, in Ebersol's book, two statements contradict this answer. One is, changes in voltage induce current to flow in circuits containing capacitors. The second statement is, inductance has the same relation to current as capacitance does to voltage. Next question. Current in a resistor inductance circuit will decay exponentially. Current in a resistor inductance circuit will increase exponentially and decay in the same fashion. So the answer to this question is true. Next question. The ideal inductive capacitor circuit demonstrates continuous oscillation. A true, B false. When direct current has been applied to a capacitor inductor circuit for a while and the capacitor has been fully charged, all current will flow through the battery inductor part of the circuit. I have labeled this as time 0. I am representing the fully charged inductor by putting a yellow cloud around the coils, and I am representing the fully charged capacitor by the aqua color filling the space between the capacitor's plate. If the circuit is then open, a moment that I have labeled time 1, two things will happen shortly after. The capacitor will begin to discharge, and the voltage stored in the inductor will maintain the flow of current beyond the time the circuit was shut. Thus, despite that no voltage is being supplied by the battery, voltage will be available on the side of the capacitor and the inductor. In this fashion, the inductor will feed the capacitor and the capacitor will feed the inductor. Thus, the inductor will be discharging when the capacitor is empty, and the capacitor will be discharging when the inductor is empty. I hope you noted that the time we're changing in the last frames, going from time 3 to time 5. This phenomenon is called oscillation. In this frame, I have tried to simplify the concept of oscillation. So the answer to this question is A. Next question. In an inductor capacitor circuit, the frequency of the continuous oscillation can be controlled. A, true, B, false. It is important to understand that by manipulating the sizes of the capacitor and the inductor of a capacitor-inductor circuit, we can develop a circuit that would have a specific oscillation frequency. The specific frequency at which a capacitor-inductor circuit oscillate is considered the natural frequency of the circuit, and the term resonance is used for it. In this frame, I have represented the use of various size capacitors and inductors in the construction of filters. Filters built with different size capacitors and filters built with different size inductors demonstrate different resonance. Their different resonance will be translated in different filtering characteristics. To give you a theoretical and imaginative example, if a certain filtering will occur with a combination of a certain size capacitor and inductor, changing the size of the capacitor will change the filtering parameters of the given filter, and so will occur by manipulating the number of turns in an inductor. That also will change the filtering specification of the given filter. The benefit of using capacitors and inductor circuits instead of capacitor resistor circuit to build filters is that a more steep exclusion of frequencies can be achieved by the use of capacitor inductor circuits. So the answer to this question is true. Next question. An inductive capacitance circuit will allow electrical activity. We already explained that an inductor capacitor circuit has oscillations, and that the frequency of the oscillations, that is the resonance of such a circuit, can be manipulated to occur at a specific frequency. The concept that we are introducing now is that wave with similar frequency as the resonance of an inductor capacitor circuit will be allowed to go unimpeded by such a circuit built with certain specifications. This quality is used, as we have said, to build EEG filters. Such filters will allow waves produced in the brain or artificial wave with similar frequency as those occurring in the inductor capacitor circuit to go through with minimal modification. If, as in this example, a circuit has a resonance of 60 Hz, that 60 Hz activity will be shunted. If the shunting occurs towards the ground, the 60 Hz activity will be removed and the EEG will have little or no 60 Hz activity. I will end this long talk by showing you an old EEG model and pointing out to you an inductor capacitor circuit in that model. As you can see, it is used to build 60 Hz filters because they allow more precise removal of unwanted frequencies than resistor capacitor circuits. So the answer to this question is A. In conclusion, inductors are important components in the EEG electrical circuitry, and they also contribute significantly to the construction of specific filters. Thank you. Thank you again.